All right, welcome back. So we're going to figure out the area of a polar coordinate graph here. Okay, so we're going to kind of review some of this stuff as we're going through it, but the whole point is to be able to do polar coordinates here. All right, so we're looking at number 7. Determine the area in one petal of the rose. R is equal to sine 3 theta. Okay, I'll usually pose the question, something like that. I'm not expecting you to know limacons versus lemniscate. You don't have to do a lot of that, okay? So, because you're gonna graph it anyway, right? Because it says sketch the curve. Hint, it's a rose. Determine your limits of integration, because that's really the whole point here. If you end up going to New Mexico Tech for Calc 3, that's I remember spending a lot of days trying to figure out where the two curves intersected and fighting with that to figure out my limits of integration. Okay, and then we're going to use the formula for area and polar coordinates and integrate. Okay, so there we go. So, and again, if you go through this, you're like, I don't remember that formula. Like, I let me know. I will write that on your final exam. Okay, so you don't have to memorize arc length or area inside of a polar coordinate. Let me know. Okay, because it's a lot to memorize. Plus, you have all of the regular, integrations that you have to deal with, like integral, secant kind of things. Okay, I will do my best. I will make sure I do not put integral of secant cubed on your final. Okay, that's just cruel. So you're not going to be doing that one. All right, what am I doing? We're going back to this, and we're going to go and we're going to write this problem down. Okay, so what do we have? We're finding the integral of r is equal to sine 3 theta. Okay, so here we go. We have r is equal to sine of 3 theta. All right, so let me do this in a couple of different ways here. So we have to find the area. Okay, so here's what we're looking at. All right, so we have a little calculus pi wedge here. Okay, we're going to take slivers here, right? This is going to be a tiny angle, okay, with some radius. Okay, pretend that's a radius. Okay. So that's what we're doing at this point. Now, to figure out the area, if you were just figuring out like a regular pie slice, if we were going to just do like, hey, how big is this piece of pizza that you have? Okay, that's called a sector. Okay, or a section. I think it's a sector. A is equal to 1/2 r squared theta. Okay. If you expand this to a whole circle, right, we're going to get area is equal to 1/2 r squared, and the angle, right, is all the way around the circle. That cancels, and we end up with a is equal to pi, 2's canceled, r squared. That's the formula that you remember. Okay, so if you have part of an angle, then you have to know this formula. Okay, and I think very few people, unless you're a real pizza fanatic, goes around trying to figure out the areas of different pizzas. Okay, but that's how you do it. Okay, so in calculus, what we're going to say is a small amount of area is equal to 1/2 r squared times a small angle, and we are going to go ahead and add those up, right? And that's how we're going to get a is equal to 1/2 integral r squared d theta. Okay, when we take the limit. All right. So that's the formula that we're going to be dealing with. Okay. So now that we know what's going to happen with our function and how we're going to do that, now it's time to figure out, like, well, what does this thing look like and what am I integrating to and from? Okay. So the way I teach my pre-calc students, my trig students, to figure out the angles, right? So when we want to graph a sine, right? You know what that looks like. And how do we teach you to do this? Well, you have the 0 point, you have the pi over 2 point, you have the pi point, you have the 3 pi over 2 point, and you have the 2 pi point. Okay. And I usually call these things anchor points because that's what you anchor your graph to. So we have 0, we have pi over 2, we have pi, we have 3 pi over 2, and then we have 2 pi. But I don't have just a plain vanilla sine wave, do I? No, we have sine is equal to, or r is equal to sine 3 theta. So what happens then? Okay, and for all of you people that said, well, can't I just memorize the period and just do it that way? This is the day you wish you wouldn't have said that. I mean, unless you still memorized it and you still have that at your hands, great. But if you didn't, you're like, what do you mean what the period is? Period's 2 pi. Okay. So what I do is I say, well, 3 theta, what does theta have to be for this sine to effectively be 0? Divide by 3 and we get theta equals 0. If I plug 0 in, we get sine of 0. We're right here. Okay. Let me make this a little bigger. Okay. Do this in a couple of different rows. Wish there was a better way to erase this stuff. Okay, so here. Okay, pi over 2. Well, what does this argument have to be for the sine to be, right, 1? So we're going to set this equal to pi over 2. Divide both sides by 3, and we get theta is equal to pi over 6. This point here, right, if I plug in pi over 6 here, put it in here, we get sine of pi over 2, and then we know that sine of pi over 2 is going to be 1. Okay, when does it go back out? So we're going to say 3 theta is equal to pi. Theta is equal to pi over 3. Okay, it's pi over 3. Yeah, it is. Okay, so this point here, this is pi over 3. Okay, what about 3 pi over 2? Right, or sorry. There we go. Okay, we have 3 theta is equal to 3 pi over 2. Like, what do I have to make theta in order for this argument to be 3 pi over 2? So we're going to say this is going to be theta is equal to, divide by 3, so that's just going to be pi over 2. Okay, and then finally, where does this thing wrap up? Okay, so we have 3 theta is equal to 2 pi. Theta is equal to 2 pi over 3. Okay. Now there's a pattern here. You may not be able to see it because the denominators are all screwed up. But this is 0. This is 1 pi over 6. This is 2 pi over 6, isn't it? That's what 1/3 is. And 1/2 is 3 pi over 6. And then we have 4 pi over 6. Okay, so when I want to graph this thing, okay, here's my theta, here's my r. So this is a coordinate axis first. We'll do the other ones in a minute. So there's my 2 pi. Well, each cycle takes it about 2/3 pi. So here's, right, we'll call that 2/3 pi. We'll call that 4/3. Nope. Yeah, 4/3 pi. And then let's erase a little bit of this. Dang it, I knew it was going to take the whole thing. So I'm trying to break this out so it looks like that. All right. And then we have to subdivide each of these regions because the cycle is going to take, right, 2 pi over 3. And we've got a middle point and then two quarter points. So here is, so I'm kind of estimating that to be the middle, and that's going to be my, right, 2 pi over 6. And then we have this point and that point. Okay, so let's see if we can't make these a little bit more useful to us. Okay, and then we're going to do middle, and then quarter, quarter, middle, and middle, and then quarter, quarter. All right. So then we'll go ahead and plot this out. So here's my 1, here's my -1. So we've got 1 up here, down here, here, and here. So my first cycle here, right? Okay, I'm going to say pretend that looks like a sine wave. All right. And then we're just going to repeat the process here. All right, and then one more time. All right. Okay, by the way, graphing like this, oh, this is theta, not x. Graphing like this of like coming up with the endpoint and then taking middles and then quarters and then eighths. You graph like that, people are going to look at you as like, wow, where'd you learn that? Just tell them, I'm just that smart. Okay. Because most people, they'll look at that like, because they don't, most people don't graph that way. They just count. Right? They just go, okay, 1, 2, 3, 4. I'm like, no. 1, back, 0, here's 4, here's 2, 1, 3. Okay, so it'll help you out with bigger graphs, but that's, that's how my trig teacher used to do it. Back when we used a compass to graph these things. Okay. All right. So next thing we're going to do, okay, is we're going to take a look at that graph and we're going to graph it as a polar coordinate. So this is my polar coordinate graph. So here's 0, here's pi over 2, here's pi, here's 3 pi over 2. Okay, and what I'm going to do is I'm going to try to sketch in. They do have like polar coordinate graph paper. I'm going to call this pi over 6. Okay, just in case we're going to need it, right? That's 7 pi over 6. Here's pi over 3. Here's 4 pi over 3. That's 3 pi over 3, so that's 4 pi over 3. And then we're going to have, that's terrible. All right, so it's 1 pi over 3. Here's 2 pi over 3. That's going to be 5 pi over 3. And then we're going to have something in halfway here. We're going to do, and it's 5 pi over 6. And over here is going to be 11 pi over 6. Okay. So there's our thing. That color. Okay. What's going on between 0 and what is this, pi over 6 here? What's going on between 0 and pi over 6? Well, the function is going from 0. The radius is going from 0. And as we sweep out along this angle, it's going all the way up to 1. Okay. Pretend these are all the same height. Right. So what's happening here is we're going out. Here's 1 unit. We're going out up to there. Okay. So when we get to pi over 6, we're at 1 unit up. When we get to 2 pi over 6, pi over 3, right, we're back down to 0. So this comes around. I didn't draw this well. So this should be entering, right, this should be coming into the origin pretty much at this angle. Okay, so I messed that up. But there we go. Okay. And then we'll just keep going here. We don't have to because we have the pedal now, but just to keep this going, we're here. Okay. And then we're going to go, this one was pi over 2, wasn't it? Yep, 3 pi over 2. So at pi over 2, the function, right, is going to be at -1. It's going to be down here. So even though, right, we should be up here with pi over 2, all of these numbers are going to be negative, so they're actually coming down here. Okay. And then coming back up to the 2 pi over 3, we're going to enter back at the origin at this angle. Okay. I promise you, I actually did practice these. And I actually had a lot of fun doing these when I was in Calc 2 and etc. So my drawings for this, they've always been terrible, but they've been better than this. Okay, can't you draw a flower? No. Okay, so here we go. And then we're just going to continue this around. Okay, this is what this is going to look like. I'm going to cheat and say, well, I know what the answer is going to be, so we're just going to write this thing down. Okay, so that's what our splitter rose looks like. It actually just repeats itself, okay, a couple of times. But all I wanted to know, what's the area of that piece? Okay, that's all I wanted to know. So, lucky I didn't put an R in here, right? So we could have an R in here, and we could figure out the intersections of these things and figure out the areas of the tips here, or the areas of this part of the blade, or lots of things we could ask about here. Okay. So they just wanted to know what the blade, what the pedal was. So our integral, right, is going to be area is equal to 1/2 integral r squared d theta. And the limits of integration, right? We start for one pedal. We started at 0. We went all the way up, come all the way down. And that was at 2 pi over 3, wasn't it? Right? That was it. No, it wasn't. It was 1 pi over 3, not 2 pi over 3, 1 pi over 3. All right. So those are our, right? Those are our limits. What the heck is r? Remember, r was equal to sine of 3 theta. Okay. So we're going to just type that in. We're going to say, well, area is equal to 1/2 0 pi over 3 sine squared 3 theta d theta. Now, you got to do a substitution, right? You can't do a u substitution. You got to do like a trig substitution in order to get this. So I know you all remember your cosine double angles. See, stuff you wanted to memorize. There it is. All right. And this is 1 minus 2 sine squared theta. It actually has a couple of them. We're going to pick this one here. Okay, so we're going to say cosine, let's do 2 phi is equal to 1 minus sine squared phi. Okay, and I will just solve for sine squared. Right, this will come over to the other side. We'll swap the sine squared and the cosine. So it'll be 2 sine squared phi is equal to 1 minus cosine phi. And then we'll divide by 2 and say sine squared phi is equal to 1 minus cosine, this one, all divided by 2. Okay. So here we're going to say, well, phi is equal to 3 theta, right? Should be a 2 there, right? Should be a 2. 2 phi must be 6 theta. Okay, that's why I didn't pick the same letter. Okay, you could have picked A, whatever, doesn't matter. So B, because A is busy on this problem. So this is 1/2 integral 0 pi over 3. Instead of sine squared, we're going to say sine squared is equal to 1/2 1 minus cosine 2 phi, which is 6 theta d theta. Piece of cake now, right? That actually is. So A is equal to 1/4. All right. And then I guess we'll just write this down for the sake of pondering an integral here. All right. So my A is equal to 1/4. The integral of 1, right? That's theta. Okay. Minus. So derivative of sine is cosine. Does it stand to reason that the integral of cosine would be sine? Sine of 6 theta over 6. What if I take this derivative, right? Take the derivative of sine of 6 theta. Well, that's cosine 6 theta times its chain rule, so times the chain is times 6. If I say 1/6, cosine 6 theta times 6, the 6's cancel, and I'm back to exactly what I had here. Okay, so I didn't use a guess and check on this one. I just used, I say wrong way. I didn't use a u substitution on this one. I just did a guess and check. Okay, and we're going from 0 pi over 3. Okay, so we got to plug that in. So we have area is equal to 1/4. And here we have pi over 3, that's theta. minus sine of 6 times pi over 3 times 1/6 minus. Be careful with the trig functions. I know a lot of these, they were polynomials, and I just put in 0. Notice I'm not doing that on this one because there's trig functions involved. And if one of them was a cosine or if there was a secant, going to be kind of stuck here, okay? So I want to be really careful with exponents, and I want to be real careful with trig. So this is pi over 3 divided by 6, and we'll see. Oh, no, we don't. We went 0, sorry. 6 times 0 is 0. What is sine of 0? It's 0. So I lied. It really was 0. Okay, here we have 1/4. Here we have pi over 3 minus 6 times pi over 3. That's 6 over 3. That's 2. 2 times pi, right? There's a sine of 2 pi here. Also 0. Right? So we're done. Pi over 12. And there is our answer for our area. Okay, that's for one petal. Okay, beautiful. There we go. You're set. All right.